Bismillahirrahmanirrahim. Okay, welcome to this course, DSP, Digital Signal Processing. In the last class, so we have just talked about the course content and other few issues like the prerequisite as well. And the prerequisite I have already mentioned, the signals and system. I believe that you have already started to gone through that topics you have already covered during the course signals and system. Okay, today we'll start the introduction of the DSP. Okay, so there is no limit of the introduction, though I have given the name as an introduction. Okay, so very few, very basics of a few definition first of all, and then time to time we'll describe some things that should be known or understood from the student point of view as well. Okay, so first of all, what is a signal? So this is just a definition. A signal is anything we can see, hear, observe, or measure using some machine or by any means. Okay, so that is called a signal. So the examples could be very simple to observe, like the speech, audio, light, radio, TV signal, radar signal, temperature. From the biomedical sense, ECG or EEG. ECG stand for electrocardiograph, and EEG stand for encephalogram, so electroencephalogram. So those are the examples, common examples of a signal, different sort of signals. What is the meaning of a signal? What is the meaning of a signal? A signal is the carrier of information. Here, this term is very important, which is information. If we don't have any information in the signal, that is known as noise. Okay, so that is the difference between the signal and the noise. In case of noise, noise is also one sort of signal. Let's say NT. This is noise signal. Noise is also one kind of signal. It might happen that noise is a signal for some other person, not for you. For example, we have DSP class now. So these audio signals, it has been recorded for the future reference. And you may have another signal for, let's say, XYZ courses that is not belongs to the 4th year. Then that course audio record is basically noise with comparing with the DSP course, because in the DSP course you have the information what you are looking for. For the other courses, okay, it might be there might be some information for you, or otherwise if I have some extra thing over there, so for the DSP, let's say DT, this is the signal, and there's from the other courses OT, this is other courses, this is basically noise. So the information is an important fact to identify the signal. So in case of signal, as we have given the example before, electrocardiograph or cardiogram, ECG, contains the information related to the sickness. And this is from the domain of medical diagnosis. So for the medical diagnosis, we are doing a lot of tests. And the most of the cases when we have done the image processing or the imaging, that is beyond the area, that is inside the area of DSP, digital signal processing, and we can do the medical diagnosis with that. Another example, voice contains information about who is speaking and what is spoken. By these two terms, who and what, we can identify the speech recognition and speaker recognition. This is a very common application of DSP. Let's say I have some voice recording. From this voice recording, all the signals we can represent by XT. This is an analog signal. Now our task is to find who is the speaker. So you need to find the name, and after finding the name, you need to also find what was the content. That means the content of the signal, whether this is spoken in Bengali. If it is in Bengali, whether it is what is the content, like it is a lecture or this is a song or whatever the things. Okay, you need to find the content. Definitely for that one, you need some reference signals. If you want to find some person, of course, you need to store some value beforehand. Okay, so hopefully during your laboratory classes, you will find these kind of things where you need to operate, or you need to go through this speaker and the speech recognition. Okay, for this case, when we are talking about this speech and speaker recognition, we need both correlation and also frequency domain analysis of the system. Okay. Okay, do you have any idea? So how we can find a speaker? Any idea? Just this is not supposed to be answered at this moment, but do you have any idea how to recognize the speaker? What is the key factor?
So we all have our individual frequencies.
Okay, thank you for your answer. Before giving any answer, please raise your hand so that I can understand who wants to give the answer. Okay, thank you. Yeah, your friend already mentioned that based on the frequency. Okay, sometimes when we are talking about frequency, this is very important. That means you have a signal. Mostly we have seen it in the time domain. That's why we represent this like xt. But when we try to see this signal in the frequency domain, we are representing by, let's say, xf, where f is the frequency. Let's say x omega, where omega is the frequency. Sometimes you can write xf, where f is the frequency. Just for the simplicity, I'm just drawing this. So this is in the time domain. This is in the time domain where this represent t, and this represent the amplitude of that signal. And here, this is the frequency, where this is the amplitude in this y-axis. This is the amplitude of that signal. And in the x-axis, that is omega for different frequencies. So what are the frequency component we have? So your friend already mentioned that, let's say the person name is A. For A, we have this voice signal. And from there, we can find that, okay, the frequency representation looks like this. This is the higher frequency, and this is the lowest frequency. Lowest frequency is 0, that is the DC value, and this is the highest frequency. Do you have any idea what could be the highest frequency of a typical voice signal? For a typical voice signal? So this is omega, the frequency, and this is analog frequency. Let's say analog frequency. Do you know what is the maximum frequency? Any guess? If you could raise your hand, yeah, 150. 150, please unmute your mic and you can say.
22,000 hertz.
20?
2,000 hertz. Kilohertz, sorry.
22 kilohertz or 2 kilohertz?
22.
22 kilohertz.
Yes.
Okay. Yeah. 63.
Sorry, is it 4 kilohertz?
That is 4 kilohertz. Hey, Okay, please put down your hands. Fine. Sorry, 180.
Yes, 20 kilohertz, sir.
20 kilohertz. Excellent. Okay, thank you for your participation. Yes, according to the literature review, this is 20 kilohertz. That is the maximum. Okay, and it is very interesting to know or make this point noted that for the female, the frequencies are higher than the male. So this is a typical statistics. And when people are saying like E like sound, then we have the higher frequency values. Okay, so almost 20 kilohertz is the highest one. Yes, the 22 you have mentioned 22 kilohertz. Yes, very close to 20 as well. So thank you for your participation. Okay, what about 4 kilohertz? There is the information. Yes, most of the information, most of the valuable information of your voice is contained inside 4 kilohertz. So why this information is important? This 4 kilohertz, why this is important? Because yes, after a few minutes, we may see that in case of signal processing, in case of DSP, it has a great impact. Whether you took the signal with 20 kilohertz or you took the signal with only 4 kilohertz, there is a big difference. That means most of the cases, what we have done, we are putting a filter which will help us to take only the signals up to 4 kilohertz, and then we can process it. What about the other things like this domain? What about this? These also have some information, but you can even neglect those things, and eventually you can't find any problem with the or distortion in the signal. It looks almost like the same as the original on. And in most cases, it is also a good practice. Why? Because in the higher frequency, you may also have a lot of noises. Okay, so those are the two facts. I'll repeat the things again when we'll talk about the time domain to frequency domain calculations and some applications of that. Okay, so of course, by knowing the frequency, we are talking about the speaker recognition. By knowing the frequency, you might know about the person, but it is not always possible. It might have that the total frequency components are similar, but what about the pattern? There is also called the pattern. So you need to know about the pattern of that signal by doing the research. Okay, so we have a lot of scope on that issues. Okay, another example. So by having these kind of examples, I try to make you understand that why the DSP course is important, why we should go through this course, why it is mandatory for the electrical engineers. If I mention this, before 20 years back, these courses like DSP was not a mandatory course for the electrical and electronic engineers. But however, nowadays, it is not only mandatory for the EEE student, it is also mandatory for many other discipline. For example, computer science and engineering as well. They are supposed to read this course. So this is so important for the digital domain, and this is also a modern subject. Why this is a modern subject? Okay, let's say if I ask you, can you send SMS with your smartphone? Everybody should give the answer yes, because this is a smart technique or this is a modern technique. So you should know how to send SMS by your smartphone. Definitely, I'm giving a very simple example. I might ask you that, can you send email by your smartphone? And hopefully everyone can do that. And it is the demand of the society that, okay, you as an engineer or as a social person, as a smart person, you should do that. Similarly, as an electrical engineers, you should have the basic or the fundamentals of the DSP. Otherwise, it is very awkward for the engineers. Okay. Okay. However, I'll talk about the radar, radio detection and ranging. Okay. The signal contains information about the target. Probably I have talked about this in the last class. That means you have the antenna. So let's say this is the antenna. From the antenna, you are the sending signals. You are sending signal in a different direction. Let's say you have an object. So whenever you have the object, there will be some reflection. So you have the sending signal. Let's say you have the sending signal and you have the received signal like this. Then you can do the correlations between this, by which you can understand whether this is your own signal back or this is a different signal. It might happen that there is a different signal. It is not your signal. It might be like signal like this. Okay, there are some other signals. In that case, the correlation will tell you that, okay, whether this is your signal or other signals. It might happen. Okay, the object, if this is an aeroplane, it can also send some signal. So if it is a unknown signal, you can also find it by the correlation. So the correlations give you two things. One is whether this is your own signal, number one, and instantly it will also be checked whether if that is your own signal, what is the distance and how far the object is. And as you know that this technique, that means the radar technique, has been invented by the British scientists during the World War II. World War II. And this is a great invention during that period of time, which actually gives the uphold on that during that war. So they have put those antennas, that means the radar antennas, the periphery of their seas. And when the Russian want to attack to the British or these British colonies, then they already know that there are some objects are coming through. At that moment, Russian-based or the Russian-based countries don't have this kind of technique. That means the radar. So the radar technique, one of the key issues which actually make the difference in case of World War II. So that is the history. In each and every war, there would be some invention. In World War I, what was the key invention? Do you know that? During the World War I, the submarine is one of the key issues which actually make the which makes the factor decider between two parties. Okay, so in case of any wars, people are giving more money. That means the governments or the countries are investing more monies for this kind of weapon or techniques. So radar is not a weapon, but this is a technique. And the similar is also true for the sonar. So in the sonar technique, you can also catch whether is there any ship or other things underneath of the water surface. So we are using the radar technique to avoid the accident for the airport navigations and also to defend the country. So you can defend your country for a better purpose. Okay. Okay, as you know that there is a technique called the stealth that has invented by USA, and due to that technique, even radar can get the image of the obstacle of the or the aeroplane, because in case of stealth, the surface was very rough, as well as they can change their surface. For example, if I have this kind of surface, let's say, and this is the antenna, in that case, you are sending the signal and it will reflect it back. But if this surface is like this, let's say the surface is like this, what will happen? The signal will not reflected back, so it will goes in the other direction. It will goes in the other direction. So that is how the stilt can change the direction of the radar signal, and it is very difficult to get the image of the stilt. However, you can get the signal. Okay, you need to put more radar surround the park or somewhere else so that you can also get this kind of signals. If you can catch those signals, then you can say, okay, there are some vehicle and probably that is a stilt. Okay. Biomedical images contain information about the authenticity and authentications. For example, face images, fingerprints, eye dish, and the vein. Most of them are now used for the security purposes. And for highly secured devices in the banks or the vaulters or the offices, nowadays we are using these kind of things for security checking or security pass. This is very popular nowadays. All are belongs to the digital signal processing. Major application areas, I'm just listing few of those just to give an idea what we are talking about and what is our domain. The image processing, it's a very vibrant area. Instrumentation and control. Currently, the industries are using all sort of controlling devices known as digital control. So digital control. Probably you have the course this semester, control system. So at the end or any between any times, you will get some lectures on digital control as well, hopefully. Speech and audio, I have already mentioned that. Military application, telecommunication. So that the core part of the telecommunication is DSP. So if you want to be a good engineer in the telecommunication domain, you can rely on me that you need to be very smart on DSP. You need to be you need to have a very depth knowledge on the DSP. You need to understand the process very precisely. Industrial applications, I have already mentioned the medical applications. There are a lot of medical applications. Why this is so important? Because as you know that for the medical applications, people are investing more and more. That's why in the biomedical engineering domain, if you are looking for scholarship, there are a lot of scholarship in the biomedical engineering domain because people are investing more money for the health purpose, health security, and health diagnosis and the disease diagnosis purpose. And in case of medical purposes, we have the tools. You need the controls, precise controls. There are some image processing, and there are a lot of image processing. You know that it's mentioned that 50% of the diagnosis now based on the image processing. So image processing is a huge domain. If you only specified or focus on the medical images. Of course, for the scientific purpose, we need the digital signal processing as well. During the session, if you have any question, please raise your hand so that I can give you the floor. Now the question is, what is signal processing? We have already learned about what is signal. Now, what is processing? The purpose of signal processing is to make it easier to extract useful information. So there are a few things. So we want to make our life easier to extract useful information. So information should be there. Without the information, that is not a signal. So you must have the information. Now from the information, you need to extract the useful information. For this purpose, what we can do, we need to implement some techniques, and those can be listed as signal enhancement. So you need to enhance your signal. Sometimes you need to signal restoration is needed, signal reconstruction, signal synthesis or synthesis, signal estimation, and prediction. In upcoming section, we have given some example of all the sections. Okay, so before going to that, so just to repeat the things again, the signal processing, the purpose of the signal processing is to make your life easier or make the task easier to extract useful information. So that is the key thing in useful information. So how do you can extract the useful information from the signal is known as the signal processing. That is very sweet and sound, precise definition of that one. After signal processing, we can extract more important information which helps to recognize, aware, and make a decision. So after signal processing, you can take your decisions. Okay, for example, this is very simple example. This is not signal processing, but this is a data processing. Again, this is a part of the signal processing. So for the COVID-19, we are getting a lot of information. So we are getting information. So the death rate from, let's say, from 60 and above, then 50 to 60, then 40 to 50, 30 to 40, and so on. So what is the death rate? So we can find those numbers. So finding those numbers, after finding those numbers, we can take the decision who should get the vaccine first. Of course, the elder people should get the vaccine first according to the percentage of the death for COVID-19. So that is the decision making. You can also recognize something. You can also recognize something. Okay, this might be a difficult example for you, but have you heard about the DNA matching? Okay, so this is the very common techniques like nowadays called DNA matching. So by DNA matching means you want to recognize something. So we have, there is a X DNA. X means this is an unknown DNA, and you have, there is some person like A, we have the DNA from there. Now we need to match those things. There is a called the microRNA. This is a microRNA. This is only the basement like this, based on different color coding. Based on different color coding, where this color coding means, okay, let's say makes like this. You have some color coding. Based on this color mapping, you can understand how much or how close closer relation between X and A. In that way, even you can find the relation between, let's say, a person, let's say a very famous person in the ancient time. What could be the name? Please mention any name from the ancient time, like Newton. Okay, so from the Newton's DNA, you want to match your own DNA. So your DNA is A, and from the Newton's DNA is N. Now you can even match with this. And your friend is B, you can also match with this. And then you can find the relation between these two, whether you are closer to Newton or your friend is closer to Newton. It is possible now by the DNA mapping. Okay, so this is called the recognitions or recognized the things. You can aware the situation, as I have already mentioned that like radar. By using the radar, you can do that things as well. Okay, now one by one, what is signal enhancement? From the name, you can understand that the signal amplification in the radio, TV signals, even for the human ear. So we have the radio signal. Let's say the signal amplitude is very low. You can put it through a device, and after that the signal is very high, this amplification is called the enhancement. This is not only for the radio TV signals, it can be also for the images. So it can enhance the quality of the filter. For example, it looks very blurred, then you can make it very bright of the images. Okay, so if you are interested in the image processing, probably in our laboratory classes, you will face some problems to enhance the images, then you will get the idea. This is enhancement. Signal restoration. One example, restore a signal computed by noise, corrupted by the noise and the useless background. So you want to restore the signal back. So you have your original signal and you have some noise signal over there. Okay, so that is corrupted by the noises. Now you are putting a filter. Through the filter, you have your original signal back. And this is called the signal restoration. So you are restoring your signal back to an original signal. This is one of the example. Then signal reconstruction. So those are the key module of the signal processing, what we have done for the processing. The signal reconstruction. This is a very important thing. For example, computerized tomography. I'm not sure about this, whether you have any experience on CT. CT is nothing like 3D X-ray. So this is a 3D X-ray. Why this is a 3D? Let's say this is the human. So we are putting this X-ray, and there is the plate where you are taking the images. This is 2D, and then it is rotating. So this one is rotating and your target is also rotating. The human will remain stand still. So you are taking a lot of 2D images, and then there is an algorithm called backpropagation. By using the backpropagation, you can show the images with a 3D mapping, and that is called the CT, computerized or computer tomography. Tomography means a imaging of a volume. So you can image of the volume. It might be very easy to understand that a reconstruction of 3D images from different 2D views. Actually, when the 3D images or 3D movies are formed or captured, it actually captured only the 2D views. Then it will be simulated in a way it looks like a 3D one. During my master's, one of the courses I have done based on this 3D image or 3D movie making. There I have seen that, okay, for a particular images, we are putting 3 cameras. This is one. This is, let's say, in 120 degree, make it like this. And so 3 cameras we are putting in 120 degree apart from each other, and that makes the this will get 2D image. This is 2D image, 2D image, and combinedly we have a 3D picture, and this is known as the reconstruction. So you can reconstruct the image from the 2D images, which looks like a 3D one. It has a huge application in the biomedical domain, the computerized tomography, as well as the movie making or visualization of the fact. Signal synthesis is now a very hot topic. You can synthesize a person. Okay, so you can synthesize a hero, a movie hero, or a person is a very popular person. You can synthesize that one. You can synthesize a news reader as well. So you can synthesize the speech. You can synthesize the person as well, and that is why sometimes you are hearing some like voice from, let's say, from the Laden, And people are telling that no, this is not the voice from the Laden, it is a synthesized voice. And nowadays this is a very popular or very contradictory issues. In a sense, you can see some person, but eventually that might be synthesized with some other person's nature. So that's why it's very difficult to say which one is true and which one is false. And for the gaming purpose as well, make virtual world. So you can make the virtual world. That is also the synthesizing part as well. Signal estimation is a very big domain. For example, you can estimate the weather having different data. You have 50 years data. From the 50 years data, you can predict 2021 for any country. Like if you have 50 years data for BD for Bangladesh, then on 2021, what will happen? You might predict the scenario, or with some other information as well. So this is signal estimation. There is a big domain called stock prediction, that is stock exchange prediction. You know that there are some buying rate and selling rate. So if you know that it will increase the rate within a couple of days, then you can hold your stock or share, and after a few days you can sell it. And for that one, you can do some signal processing mathematics. You can use some prediction mathematics, and probably you will be surprised to know that most of the genius people from the MIT or the university, like those who are very special with DSP or with the mathematics, they used to find or used to build some algorithm for stock prediction. Why that is so? Because it can be sold with a lot of money. Because the businessmen are always happy to give a lot of money to buy this kind of prediction algorithm from those people. Okay, that is in a nutshell the domain of the digital signal processing. So we can have the control over those domains if we have a good understanding on digital signal processing. At this moment, do you have any question or comments? Okay. Then we can move to the next section. This is the concept of frequency in continuous time first, and then for the discrete time signals. I believe that you have full control on the continuous time domain. However, I would like to express it here again so that you can make a comparison between the continuous time to the discrete time domain. Continuous time signal. I have given an example, very simple example. This is XAT. This small a, that means XA, this small a is representing, this is an analog signal. This T represent, this is in the time domain. Each and every part of this equation you should understand practically, visually with the graphical representation. That will help us. Okay. Then A cos omega t plus theta, where t can be from minus infinity to plus infinity. It shows that this is an infinite signal. Minus infinity, what is the concept of the minus infinity? T0 means this is a present, and t plus infinity, that is future, minus infinity, that is past. So very simple concept from the time domain. In this equation, A represents the amplitude of the sinusoid. The omega, very important, the frequency in radians, not in degree, okay? In radians per second. Radians per second. And the theta, you can, sometimes people are using phi, okay? Theta the phase in radians. So throughout this course, whenever I will use capital omega, it shows the frequency in radian per second in the time domain. So this is the frequency in the analog domain. Be careful on this notation. So you probably understand this very easily. Okay. So I have just made two lines to represent the relation between the radians and the degrees. Okay. So as you have already know that if I have a circle like this, it actually contains the periphery. So the circumference will have twice pi r is the circumference. And the concept of the radius is like this. If we have a radian, is you have the radius like this, and let's say you are putting that same radius here r, and you are bending it to this circumference, and so you are bending that, and now you are making an r is there, and this angle is known as 1 radian. This angle is known as 1 rad. So how many times you need to put this some kind of triangle? So how many times you need to put this kind of triangle to make the whole circle? You need to make twice pi time to make the whole circle. So this twice pi radian gives 360 degree, because 360 degree is the whole degree of angle is 360 degrees. So from then we got the 1 radian is 360 degree divided by twice pi, and that gives this value, and this is equals to 57.3 degree. So always if we want to think of from the radian to degree, so this could give us enough information. So you can jump from one domain to another domain from this relation. Twice pi is equivalent to 360 degree. Twice pi radian is equivalent to 360 degree. Okay. Okay, let me ask you one very interesting question. I have found it, like, how could you find that for a circle it contains 360 degree? 360 degree. How could you find this 360 degree? Can you justify this is 360 degree? Have you ever think about this? How this is 360 degree? Any of you? Why this is 360 degree? I'm just asking. Okay, there's a yes, 76.
Because it is a circle.
Because it is circle.
Yes, I think.
Okay. Any other response? Thank you, Jubair, for your response. Any other responses? Okay. Yes, 90.
Sir, people used to think that Earth moves around the sun, rotates around the sun, or revolves around the sun for 360 days. So they thought the circle is 360 degrees, something like that. Maybe
Okay.
a complete year, a complete circuit.
Okay. This is a very good answer. Okay, so there are some. Thank you, Saifullah, ID 90, and also Jubair. Okay. Yes, there are a different philosophy based on or for this 360 degree. One of those are like this. What our friend Saifullah already mentioned, like that. For the solar year, it is 365. For the lunar year, this is 355. What could be in between? that is 360. Somebody tells that, okay, this is the point to take 360 as the angle for the whole cycle. In other literature or any other history, they have mentioned that there are some few stars. There are some stars that will take 360 days to cover the whole Earth. Because as you know that for making the direction or pointing the direction previously or nowadays, even the stars are taken into account. So in that point of view, they have the Babylonians, mostly the Babylonians make their calendar as 360 days in a year. So from there, they have taken 360 degree as a full cycle. Similarly, it is also very popular in a way that we are making our calculation with the decimal number. That means all are 10. They have taken this number, all are 6. That should be a multiplier with the 6. And if you can think of this 360 degree, it can be related with 1, 2, 3, 4, 5, 6, 8, 9, and 10. So all the numbers can be divided or can be conquered. That is a number of these numbers can make 360 apart from 7. So this is very convenient. So that's why the number system with respect to 6, there's a different name. This is our decibel system. This is a 6-based system. There is a different name. I forgot the name, so you can find it. So those are the history. So mostly, yes, they have thought that the 1 year could be very close to 360, and they found that this is easier to make the mathematical calculation. That's why they have took this angle 360 degree. If you took, okay, like a 400 degree, there is no problem. So in this case, this is 100, this is 100, like this, 100 and 100. Is there any problem? Basically, there is no problem. You can do the calculations, but the basic problem is it makes your life little bit difficult. Eventually, this is a measurement system. A measurement system just need a reference. You can put the reference and then you can go ahead, no problem. For example, how 1 centimeter looks like? Let's say this is 1 centimeter. Who tell you that this is 1 centimeter? There should be some reference, and then afterwards you can go forward. If this is 1 centimeter, then this is 2 centimeter, this is 3 centimeter, this is 4 centimeter, no problem. If you mention that this is 1 kilometer, then this is 2 kilometer, this is 3 kilometer, and this is 4 kilometer. So it's up to you when we are talking about the measurement system. But we are proposing the measurement system in such a way so that the calculation could be very easier. Okay. Oh, come to our main business, where we have mentioned about the omega. Omega is what? Try to mention that this is a frequency in radian. It can be mentioned like this, twice pi f. As I already mentioned that this is in radian, so there must have some part of twice pi. So radian will have some part of twice pi. So twice pi f is equals to twice pi f, where capital F, try to memorize this or remember this, the capital F throughout the semester will take capital F as the frequency in cycle per second or hertz. So basically what we are mentioning as a frequency, this is the frequency, capital F. But to identify the analog signal, from now on, please mention that this capital F is the analog frequency, or you can say the original frequency. Because in the discrete domain or digital domain, there is a changes or there are some flexibility of the frequencies. There is no certain original frequency. The digital frequencies are called the relative frequency. The digital frequencies are called the relative frequency. Whenever I have mentioned the question like that, find the original frequency, or the original frequency is given as 50 Hertz, it means that that is a capital F. The discrete or digital frequency is never been a original frequency. That is a relative frequency. Okay, relative frequency to what? I will explain it in the next lecture, inshallah. Okay. So be careful on the notation. What is capital omega? This is also frequency in radian. What is capital F? This is also frequency in cycle per second, or say hertz. Cycles per second. How many cycles you are propagating? So let's say you are propagating 2 cycles. Here we have 2 cycles. And what is the time? This is t divided by t. So how many cycles over time? That is our capital F. That is how we have found the things. Mostly we are talking about a single cycle. Okay, if this is t, and how many cycles you have? 1 cycles. 1 divided by capital T is our capital F, or the frequency in hertz. So by elaborating the value of capital omega, we can write a cos twice pi capital Ft plus theta, and how it looks like in the time domain. So this is the diagram. Okay, so the very simple causal signal, sinusoidal signal with a phase shift of theta, phase shift of the theta. Here a few points. Of course, you understand each and every point. Just to make the idea more clear, this is an instantaneous signal. Instantaneous signals means for each and every value of t, you will have the value. Let's say for t is equals to 0. For t is equals to 0, we have a cos theta, and this is that point. So this is t is equals to 0. This axis belongs to t equals to 0. At t equals to 0, the value is a cos theta, and you are increasing the value of t, and then you are ahead of going to this organizing this signal in the positive direction. If you are putting t is equals to minus value, you are going to the negative direction as well. What is the distance between 2 peak or 2 similar phase? I should say 2 similar phase. In that case, you will have the distance is tp. T for the peak value is equals to 1 by f. Be very careful on this notation for the time signal. Let's say I have a signal like this. So for this one, of course, where is the same phase? We are getting the same phase on these 2 points. This is the point and this is the point where we are getting the same phases. So the t would be like this. Okay. So you need to find the t. Whenever you try to find the t of a time sequences, you need to think of the same phase. So I believe that you know that what is known as the same phase of a signal. You have the same amplitude, you have the same rate of change, and the direction as well. What is the direction? Rate of change, amplitude, and direction. For example, if I have some point here and this point, there might have these things. What are the similarity? It should goes in the same direction. Let's say it is going this direction. It must need to goes in the same direction, and they have the same amplitude. Okay. And not only the direction, they have the same pace of that. But what is the pace? So from the vector diagram, they have the same length. If I made the things like this, they have this, and this point has this kind of thing, then they are not in the same phase. For example, this. Okay, if this is a signal, probably I can make the point clear. If this is the signal, of course, this point B and point A are not in the same phase. But if I draw this like this, they are in the same phase. So you need three things. One is the amplitude should be same, the direction of the precession should be same, and as well as the rate of change should be same for having the same phase of the signal. Okay, so if the sinusoid signal is periodic, then we can write this, of course, after each t time, you have the same signal back. After each t time, as we have that, after t seconds, you have the same signal. Again, after twice TP, you have the same signal. After thrice TP, you have the same signal. That's why it is known as the TP is the time period of that signal. It can be also mentioned in this way. That means the sinusoidal signal as complex exponential signal. Okay, so what is the notation? I'm writing it here again. XAT is equals to A, the amplitude, e to the power j omega t plus theta. So how the xt looks like in the time domain? It looks like, let's say we have done it before, so we know that. Okay, so this should also looks like the same. Can you draw this? I'm asking this question. Can you draw this? A e to the power j omega t plus theta, or if I make it very simple, like A e to the power j omega t, can you draw this? And from there, can you prove that it is equivalent or equals to our xt? Okay, so in the next class, I will try to show it how it would be similar to that. Okay, let me do it now because it will help you to understand the fact. Okay, let me just think of, this is our XAT, the analog signal is equals to A e to the power j omega t for the simplicity. Forget about the phase. Okay, first of all, this one. How it should be looks like, since this is there is no phase difference, it should be a cause signal. During this lecture, if you find anything difficult, just raise your hand. Okay, so this is nothing but a cause signal. Now what we can do, this is in a Cartesian plane. Okay, let me take another color. So at t is equals to 0, that means we are at this moment t equals to 0. At t equals to 0, what happened? E to the power 0. E to the power 0 means 1, and you have only, so e to the power 0, that means the theta, this part, the theta is 0, and the amplitude is A. So theta is 0 and amplitude is A. So let's see, this is that value. So this is what? This is your A. And with considering this in the linear domain, what I can do, I can take another color. So I can put this point to that. Okay, I'm marking this to that point. So this is the amplitude. amplitude direction. This is basically y direction, and this is basically t direction. So t is equals to 0 at this moment. And what we are doing here, this is the real and this is imaginary. But this is starting from this is theta is equals to 0, and this is 90, and so on and so forth. So it will increase the value. Okay, now when you are progressing, so that means for higher value of t, in which direction this point, this A will rotate. Since this is a plus, then it will rotate in the anti-clockwise. So for positive, it will rotate in the anti-clockwise. For example, maybe in some point, it will be here in some point. Okay, so of course, the amplitude is A, where t is more than 0. And what is the amplitude now at this moment? Let's say this is the amplitude. I'm plotting this amplitude. So we are at this moment. Now, when it is proceed 90 degree, so this is 0, this is 90. Okay, so 90 means the A will proceed in this direction, and it will be on the imaginary axis. So what is the magnitude in the time domain in that point? In that point, it will definitely gives you 0, because the amplitude will be 0. Similarly, you can understand what will happen when it is in this direction. At that moment, we are finding this value over this. What will happen when it is on this direction? It will give you the value, the maximum in the negative direction. If you proceed on the same way, you can have this, you can have this, you can have this, and eventually what you can find, try to understand, you will find this kind of signal, isn't it? I'm actually drawn like this, okay, from this point to this point. If I want to make it clear, from this point to this point, the maximum to the 0, and then again 0, the maximum, and then 0. So this part, now you can see that, okay, this time domain signals is equals to these time domain signals. So how we got that? We have got this from this. So this is how graphically you can represent that. Okay, xat is equals to a e to the power j omega t. Have you understood the things? Have you got the point? How we have drawn this?
Yes, sir.
Okay.
Sir, I think it would be better if you can do it once again.
Sorry, loudly, please.
Sir, I think it would be better if you can please explain it once again.
If I can repeat the procedure.
Yes, sir. That,
Okay. So you can just I have definitely uploaded the video. You can see this video again. If it is still, if you have any problem, in the next class I will talk about this, inshallah, no problem. Now you can try this with theta as well, and then that will make some shifting. Okay, so you can try yourself to understand the shifting process as well. Okay. Similarly, xat is equals to this one, and it can be also written like this. So according to the Euler's formula, we can also write like this. Okay, I should stop at this point. From tomorrow's lecture or the next lecture, we can talk about this. Definitely, I will try to show it also graphically, how this equation actually give you this kind of signals, eventually this kind of signals. So that graphical representations are always helpful for understanding. Okay. If you have any question or comments on today's lectures, you are most welcome. Otherwise, we can finish our lecture today. Hopefully there is no other question. So thank you very much for your participation.